Hello there, and welcome to Worlds Beyond Seen. I'm glad you found your way here tonight, to this quiet corner where we explore the extraordinary stories written into the very rocks beneath our feet, the ancient dramas that shaped not just our world, but us. Tonight, we're going to journey back through time, not just a few centuries or even a few millennia, but 74,000 years into our past, to a moment when the Earth itself opened up and nearly ended our story before it had truly begun, to a catastrophe so immense that it reduced the entire human population to perhaps just a few thousand souls clinging to survival in scattered pockets across Africa and Asia. This is the story of the Toba Supervolcano, the largest explosive eruption our planet has witnessed in 2 million years, an event that turned day into night, poisoned the air, and plunged the world into a volcanic winter that would test every living thing to its breaking point. Some scientists believe it brought our species to the very edge of extinction, creating a genetic bottleneck so severe that we still carry its signature in our DNA today. But this is also a story of resilience, of ingenuity, of the remarkable adaptability that would define our species and carry us from those dark days to every corner of the globe. Because somehow, against all odds, we survived. Before we begin this journey, I'd like to invite you to like this video and subscribe to the channel to support more explorations like this one. Your support helps us continue bringing these stories to life, these moments when the deep past whispers its secrets to the present. So settle in. Perhaps you're listening as the day fades into evening, or maybe you're already in that peaceful space between wakefulness and sleep. Either way, let's travel together, back to a time when our ancestors looked up at a sky turned black with ash, when they huddled around fires that were their only light in a darkened world, when they wondered if the sun would ever shine again. Let's go back to the day the world changed. Chapter 1. The day the world changed. Imagine, if you will, a morning 74,000 years ago. The sun rises over what we now call Sumatra, an island in Southeast Asia where the Indian Ocean meets the Pacific. It's a landscape of dense tropical forests, steaming with moisture, alive with the calls of birds and the rustling of unseen creatures in the undergrowth. But beneath this verdant paradise, something is stirring, something that has been building for centuries, millennia even. Deep in the earth, 30 miles below the surface, a chamber of molten rock has been swelling, growing, pressing against the overlying crust with unimaginable force. This is not just any magma chamber. It's colossal, containing enough molten material to fill a small ocean. The pressure has been building for so long that the rock above has begun to fracture, to crack, to strain under forces that could reshape continents. And then, on one unremarkable morning, it gives way. The eruption begins not with a single explosion but with a series of them, each building on the last. The ground splits open along massive fault lines, and from these wounds in the Earth's crust, a column of superheated gas, ash, and pulverized rock shoots into the sky. But this is no ordinary volcanic plume. This column rises at speeds that defy comprehension, accelerating upward until it punches through the troposphere, through the stratosphere, reaching heights of 20 miles, 30 miles, perhaps even more. The roar is beyond description. It's a sound that would carry for hundreds of miles, a deep, fundamental note that shakes the very foundations of the island. Trees nearest the eruption simply disintegrate, turn to ash in milliseconds by temperatures hot enough to melt rock. The ground heaves and buckles as billions of tons of material are expelled from the depths. And this is just the beginning. The eruption lasts not hours but days, perhaps as long as 2 weeks of continuous, cataclysmic violence. Wave after wave of pyroclastic flows, superheated clouds of gas and rock fragments that can reach temperatures of 1,000 degrees Celsius, race down the mountainsides at hundreds of miles per hour. Nothing in their path survives. Forests are incinerated, rivers boil away, the very landscape is scoured clean, buried under hundreds of feet of hot ash and pumice. But the true horror of Toba is not what it does to its immediate surroundings. It's what it does to the entire planet. As that immense column of ash and gas punches into the stratosphere, it spreads outward, forming a massive umbrella that begins to encircle the globe. Carried by high-altitude winds, volcanic ash falls like toxic snow across South Asia, blanketing India, Pakistan, Bangladesh in layers that will eventually reach 15 centimeters thick. In some places, the ash layer is so dense that scientists can still identify it today, a grey-white band in the rock record that marks this moment of planetary trauma. But ash is the least of the world's problems. Mixed with all that pulverized rock is something far more insidious: sulfur dioxide. The Toba eruption releases somewhere between 100 million and 1 billion tons of this gas into the stratosphere. Up there, far above where weather happens, far above where rain can wash it away, the sulfur dioxide reacts with water vapor to form tiny droplets of sulfuric acid. These aerosol particles are invisible killers. Each one is so small that billions could fit on the head of a pin, but collectively they form a veil that wraps around the entire planet. And they have one profound effect: they reflect sunlight back into space. Within weeks, people living thousands of miles from Sumatra begin to notice the changes. The sun, when visible at all, appears dimmer, redder. The sky takes on strange hues at dawn and dusk, paintings of blood and fire. But the aesthetic changes are nothing compared to the temperature drop. Current climate models suggest that global temperatures plummet by 3 to 5 degrees Celsius in the years following the eruption, with some regions experiencing drops of up to 15 degrees. That might not sound like much, but it's the difference between life and death for countless species. Monsoons fail, growing seasons shorten or disappear entirely. In higher latitudes, snow that would normally melt in summer persists year-round, setting in motion a feedback loop that could trigger an ice age. This is what scientists call a volcanic winter, a period when the sun's warmth is blocked so effectively that the planet itself goes into a deep freeze. And the Toba volcanic winter doesn't last months. It lasts years, perhaps a decade of dimmed skies and failed crops and slowly mounting desperation. For the humans living through this, scattered in small groups across Africa, the Middle East, and Asia, the changes must have seemed apocalyptic. Imagine being alive in those years. You're part of a band of perhaps 50 people, hunter-gatherers, who have lived in this valley for as long as anyone can remember. The stories passed down by elders speak of the rhythms of the seasons, when the rains come, when the herds migrate, when certain plants bear fruit. But then, over the course of just a few years, everything changes. The rains don't come when they should. The herds grow smaller, sickly. Plants that once grew in abundance wither and die, and that strange haze in the sky never seems to lift. Night after night, you gather around the fire with your family, and you can feel it in your bones, this sense that the world is broken, that something fundamental has gone wrong. You don't know about volcanoes. You've never heard of Sumatra, have no concept of tectonic plates or magma chambers. All you know is that the world has turned hostile, and you must adapt or die. And the truly terrifying thing, the detail that still sends shivers through modern scientists who study this event, is that this may not have been the worst of it. Because Toba didn't erupt into a stable, pleasant climate. It erupted right in the middle of one of Earth's periodic plunges toward glaciation, a natural cooling trend that was already putting stress on ecosystems worldwide. The eruption was, in essence, a kick delivered to a system that was already teetering on the edge, and the result, according to some scientists, was nearly the end of our species. The hypothesis that emerged in the late 1992, championed by anthropologist Stanley Ambrose and others, suggested that the Toba eruption created a population bottleneck so severe that the entire human population worldwide might have crashed to as few as 3,000 individuals. Some estimates go even lower, suggesting that as few as 1,000 breeding pairs might have survived. Think about that for a moment. 1,000 breeding pairs. If that figure is accurate, then every human being alive today, all 8 billion of us, descended from fewer people than currently live in a small town. We came that close to extinction. The evidence for this bottleneck comes from an unlikely source: our genes. When geneticists examine the DNA of modern humans, they notice something strange. Compared to other ape species, to chimpanzees or gorillas, we have remarkably little genetic diversity. It's as if all humans alive today descended from a relatively small ancestral population that lived sometime in the not-too-distant past. When you run the numbers, when you calculate backward through mutations and genetic drift, the timeline points to a severe population crash occurring roughly 70,000 years ago, right around the time of Toba. Coincidence? Perhaps. But the timing is suspiciously perfect, and when you add in the physical evidence, the layers of ash found at archaeological sites, the changes in the climate record visible in ice cores and lake sediments, a picture begins to emerge of a world pushed to the brink. But here's where the story gets interesting, where it shifts from simple catastrophe to something more nuanced, more hopeful. Because as scientists have continued to dig, literally and figuratively, into the Toba event, they've discovered something remarkable. We survived. Not just barely, not just by hiding in caves and eating whatever scraps we could find. Recent archaeological evidence suggests that in some places, humans didn't just endure the Toba eruption, they actually thrived in its aftermath. They innovated, they developed new technologies, they adapted their behavior in ways that would ultimately make us one of the most successful species the planet has ever seen. How did we do it? How did a species that was, evolutionarily speaking, still quite young, still quite similar to its ancestor species, manage to survive an extinction-level event? What adaptations, what strategies, what lucky breaks allowed us to cling to existence when so much else perished? That's the mystery we're going to explore tonight. A mystery that takes us from the volcanic islands of Indonesia to the caves of South Africa, from the highlands of Ethiopia to the river valleys of India. A mystery that involves volcanic glass no thicker than a human hair, genetic code written into every cell of your body, and stone tools that still bear the marks of the hands that crafted them 74,000 years ago. But before we can understand how humans survived, we need to understand what exactly they were surviving. We need to look deeper into the nature of supervolcanoes themselves to understand the forces that created Toba and the devastation it wrought. So let's descend into the earth, to where continents collide and magma churns, to the processes that created one of the most powerful weapons in nature's arsenal. Chapter 2: Understanding Supervolcanoes. When most people think of volcanoes, they picture something like Mount St. Helens or Mount Vesuvius, cone-shaped mountains that periodically erupt, sending lava flowing down their sides, creating spectacular but localized destruction. These are the volcanoes of disaster movies and dramatic photographs, impressive to be sure, but ultimately containable. Supervolcanoes are something else entirely. The term itself is relatively new, coined in the early 2000s to describe volcanoes capable of producing eruptions at least 1,000 times larger than Mount St. Helens. These aren't mountains at all. In fact, supervolcanoes can be remarkably hard to spot until you know what you're looking for, because their most distinctive feature is what's left behind after they erupt. A caldera, a massive depression in the earth, where the ground collapsed into the emptied magma chamber below. Toba's caldera is one of the largest on Earth. It measures roughly 100 kilometers long by 30 kilometers wide, a depression so immense that it now contains an entire lake, Lake Toba, which is itself the largest volcanic lake in the world. When you stand on its shores today, looking out across the peaceful water with its fishing boats and tourists, it's almost impossible to imagine that you're standing inside the scar left by the most violent explosive eruption in the last 2 million years. But to understand how Toba came to be, we need to understand the geology beneath Indonesia, the massive forces that have been shaping this region for millions of years. Indonesia sits on what's called the Ring of Fire, a horseshoe-shaped belt around the Pacific Ocean where tectonic plates collide and volcanic activity is intense. Specifically, the Indo-Australian plate is being pushed underneath the Eurasian plate in a process called subduction. As the Indo-Australian plate descends into the mantle, it begins to melt, and that molten rock, lighter than the surrounding material, starts to rise. But it doesn't always make it to the surface immediately. Sometimes, that rising magma gets trapped, pooling in chambers deep underground where it can sit for thousands, even millions of years. And as it sits, it cooks the rocks around it, incorporating more and more material, growing larger and more chemically evolved. The magma beneath Toba is what's called rhyolitic, a fancy geological term meaning it's rich in silica. This matters because silica-rich magma is viscous, thick like honey, rather than runny like the basaltic lava you see flowing from Hawaiian volcanoes. That viscosity means gases can't easily escape from the magma. Pressure builds, and builds, and builds. Think of it like shaking a bottle of champagne. At first, nothing happens, but the pressure inside is mounting. The carbon dioxide dissolved in the liquid is coming out of solution, forming bubbles. And when you finally open that bottle, it doesn't just pour out gently, it explodes. Toba was a champagne bottle that had been shaking for hundreds of thousands of years. Geologists have identified at least 4 major eruptions from the Toba caldera complex over the past 1.2 million years. Each one was massive, each one reshaped the landscape. But the most recent eruption, the youngest Toba Tuff event that occurred 74,000 years ago, was the largest of them all. When Toba finally erupted, it expelled an estimated 2,800 cubic kilometers of material. To put that in perspective, that's enough rock and ash to bury the entire United States under a layer half a foot thick. It's about 2,000 times the volume of material ejected by Mount St. Helens in 1980. It dwarfs even the 1,815 eruption of Tambora, which caused the famous Year Without a Summer and led to widespread famine across Europe and North America. The eruption was so powerful that it created a column of ash and gas that may have reached heights of 40 kilometers, punching into the stratosphere with such force that it distributed material globally within weeks. The finest particles, microscopic shards of volcanic glass called cryptotephra, traveled thousands of miles on high-altitude winds, eventually settling in layers so thin you need a microscope to see them. But it's not just the volume of material that makes a supereruption so catastrophic. It's what that material does once it's in the atmosphere. As we discussed earlier, the sulfur dioxide is the real killer. Toba released somewhere between 100 million and 1 billion metric tons of this gas. Even taking the lower estimate, that's still about 100 times what Mount Pinatubo released in 1991, and Pinatubo's eruption caused a measurable drop in global temperatures for 2 years afterward. The sulfur dioxide rises into the stratosphere, where it reacts with water vapor to form sulfuric acid aerosols. These tiny droplets remain suspended in the upper atmosphere for years, spreading around the globe and creating that reflective layer that bounces sunlight back into space before it can warm the Earth's surface. The result is a volcanic winter, a period of global cooling that can last for years. Temperatures drop, growing seasons shorten, precipitation patterns shift, and for species already living on the edge, already struggling to find enough food or water, these changes can be catastrophic. But there's another effect that scientists have only recently begun to fully appreciate. Those sulfate aerosols don't just reflect light, they also interfere with ozone formation in the stratosphere. The ozone layer, which normally shields the Earth's surface from harmful ultraviolet radiation, can be severely depleted by a supereruption. A 2021 study using sophisticated climate models found that the Toba eruption likely caused severe stratospheric ozone depletion, particularly over the tropics. For more than a year after the eruption, UV radiation levels at the Earth's surface could have been dangerously high, adding yet another stress to ecosystems already reeling from temperature drops and failing monsoons. Imagine the compounding effects. First, the immediate horror of the eruption itself, for anyone unlucky enough to be in the region. Then, the ash fall, smothering vegetation and poisoning water sources. Then, the dimming of the sun and the onset of winter conditions, even in tropical regions. And finally, Even when the skies begin to clear, the sun that returns carries with it dangerous levels of radiation that can damage DNA, cause cataracts, suppress immune systems. It's the kind of multi-layered catastrophe that could drive species to extinction. And according to the original Toba catastrophe theory proposed in the 1990 seconds, it nearly did. The theory, as originally formulated, suggested that the Toba eruption triggered a volcanic winter lasting 6 to 10 years, followed by 1,000 years of cooler than average global temperatures. This extended cooling period would have caused massive die-offs of plants and animals, collapsing food chains and forcing human populations to contract into small refugia, isolated pockets where conditions remained barely tolerable. The genetic evidence seemed to support this scenario. Studies of human mitochondrial DNA, which is inherited only through the maternal line, suggested that all humans alive today descended from a population that numbered just a few thousand individuals sometime between 50,000 and 100,000 years ago. The timing was suspiciously close to Toba. Similarly, studies of Y chromosome DNA, inherited through the paternal line, showed evidence of a severe bottleneck. And it wasn't just humans. Genetic studies of chimpanzees, orangutans, and other species also showed evidence of population crashes around the same time period. It seemed like an open and shut case. Toba erupted, the world froze, and most living things died. Only a lucky few survived, huddled in scattered refuges, barely clinging to existence until the climate recovered. But science rarely gives us simple stories, and as researchers continued to investigate, as they gathered more data from more sources, the picture began to grow more complex, more nuanced, and in many ways more interesting. Because while the genetic evidence for a bottleneck remains solid, the link to Toba has become increasingly tenuous, and the archaeological evidence, rather than showing a world devastated by volcanic catastrophe, shows something quite different. It shows adaptation, innovation, survival, not despite Toba, but perhaps, in some strange way, because of it. Before we explore that archaeological evidence, though, we need to look more closely at the climate data itself, because understanding exactly what Toba did to the world's climate turns out to be far more complicated than early models suggested. Chapter 3: Volcanic Winter and Climate Chaos. The Earth's climate is not a simple machine with simple reactions. It's a complex, interconnected system where changes in one component can ripple through others in unexpected ways, creating feedback loops and cascading effects that are difficult to predict, even with our most sophisticated models. When Toba erupted 74,000 years ago, it didn't inject its sulfur and ash into a stable, placid climate. The eruption occurred during a period of natural climate instability, right at the transition between marine isotope stage 5 and marine isotope stage 4, a shift from relatively warm conditions into a period of glacial advance. The Earth was already cooling. Ice sheets in the northern hemisphere were beginning to expand. Ocean circulation patterns were shifting, and into this already unstable system came Toba, adding its own catastrophic forcing. Understanding what actually happened requires us to look at multiple lines of evidence, each providing a different piece of the puzzle. The first and most direct evidence comes from ice cores. Scientists have drilled deep into the ice sheets of Greenland and Antarctica, extracting cylinders of ice that contain trapped bubbles of ancient atmosphere. These cores are time capsules, preserving the chemical composition of the air going back hundreds of thousands of years. When researchers examine these cores, they find layers of sulfate at various depths, markers of volcanic eruptions. By measuring the precise isotopic composition of the sulfur in these layers, they can determine not just that an eruption occurred, but whether it was a tropical eruption like Toba or something from higher latitudes. In 2021, a detailed study of these sulfate layers narrowed down the most likely candidate for Toba's signal in the ice core record. They found a massive sulfate spike dating to approximately 74,156 years ago, with sulfur isotope ratios consistent with a tropical eruption. The amount of sulfate preserved in both Greenland and Antarctic ice suggests that Toba deposited somewhere around 535 million metric tons of sulfur into the stratosphere. To put that in context, it's roughly 6 times what Tambora released, and 20 times what Pinatubo ejected. It's an almost incomprehensible amount of material to inject into the upper atmosphere. Climate models that simulate a Toba-scale eruption show initial cooling of between 3 and 5 degrees Celsius globally, with higher latitudes experiencing drops of up to 15 degrees. The cooling is most intense in the first few years after the eruption, when the sulfate aerosol layer is at its thickest. But here's where things get interesting. While the initial volcanic winter might last for several years, the climate models show that temperatures begin to recover within a decade or so. The sulfate aerosols, even at such massive concentrations, eventually fall out of the atmosphere. The sun returns to full strength, and the planet warms back up. In other words, Toba alone could not have caused a 1,000-year cooling period. Something else must have been going on. That something else was the natural climate system itself. The timing of Toba's eruption was, in a sense, spectacularly bad luck. It occurred right at the onset of Greenland's Stadial 20, a cold period associated with major disruptions in ocean circulation. These stadials are part of a regular pattern of climate oscillations called Dansgaard-Oeschger events, rapid swings between warmer and cooler conditions that punctuated the last ice age. What the ice core evidence suggests is that Toba didn't create the 1,000-year cooling period. Instead, it amplified and accelerated a cooling trend that was already underway. The eruption gave the climate system a push at exactly the wrong moment, potentially tipping it into a more severe cold phase than might have occurred otherwise. Imagine a ball sitting near the top of a hill. It's not quite rolling down yet, but it's close. Toba was like giving that ball a kick. It didn't create the hill, it didn't determine that the ball would eventually roll down, but it certainly sped up the process and ensured that when the ball did start rolling, it went fast. But even this more nuanced picture leaves questions, because while we can see the global signal, the planetary scale cooling, what really matters for understanding human survival is what happened at the regional level. Global average temperature is one thing. What people actually experienced in their local environments is quite another. And this is where the climate story becomes fascinatingly complex. Recent research has shown that the effects of Toba varied dramatically depending on location. In some regions, particularly the tropics, the cooling was significant, but not catastrophic. In others, particularly at higher latitudes, the effects would have been severe, with extended winters and shortened growing seasons. But in other areas, especially in parts of Africa, the picture is even more complicated. Some regions may have experienced cooling, yes, but the bigger impact was a shift toward more arid conditions. The monsoons weakened, rainfall patterns changed, and what was once lush forest or savanna gradually transitioned toward more open grassland or even semi-desert. This matters because humans, and our hominin ancestors generally, have always been remarkably adaptable when it comes to temperature. We're clever enough to make warm clothes, to build shelters, to control fire. What's much harder to adapt to is the loss of water and the collapse of food sources that depend on predictable rainfall. Lake Malawi in East Africa provides one of the most detailed records of environmental conditions around the time of Toba. Scientists have drilled cores from the lake bottom and analysed the sediments layer by layer, looking for changes in pollen, in lake chemistry, in the types of tiny organisms that lived in the water. What they found was striking. There's a clear layer of Toba ash in these sediments, proving that the eruption's fallout reached as far as East Africa, some 7,000 kilometers from the volcano. But when researchers looked at the environmental indicators in the layers immediately above and below the ash, they found surprisingly little disruption. The types of plants growing around the lake didn't change dramatically. The lake level remained relatively stable. There was no sudden die-off of the tiny organisms whose shells accumulate in the sediments. In other words, at least at this location, life went on more or less as before. But dig a little deeper into the data, look a bit more carefully, and subtle changes emerge. there was a shift toward more drought-adapted plant species. The proportion of grass pollen increased relative to tree pollen. The lake record suggests a gradual trend toward more arid conditions, not a sudden catastrophic change, but a slow ratcheting up of environmental stress. Similar patterns emerge from other sites across Africa and Asia. At Pinnacle Point in South Africa, one of the most extensively studied archaeological sites spanning the Toba eruption, researchers found something unexpected. Rather than evidence of human populations crashing or disappearing, they found evidence of continuity and innovation. The stone tools found in layers dating to before Toba are remarkably similar to those found in layers dating to after the eruption. The same technological traditions persisted, but there are also subtle changes, refinements in technique, new tool types appearing, evidence that people were adapting and innovating rather than simply struggling to survive. In India, at sites in the Middle Sun Valley and at Jwalapuram, archaeologists have found similar patterns. Layers of Toba ash are clearly visible, sometimes more than a foot thick, but above and below these ash layers, human occupation continues. The same types of stone tools persist across the boundary. Life, it seems, went on. Now, this doesn't mean Toba was harmless. The eruption clearly had global effects. The sulfate signal in the ice cores is undeniable. The climate models all agree that significant cooling occurred, and the genetic evidence for a population bottleneck remains solid. What's changed is our understanding of how severe and how long-lasting those effects were. Rather than a catastrophic volcanic winter that killed 90% of humanity in a few years, we're looking at something more subtle, a multi-decade period of environmental stress that contributed to, but did not solely cause, a longer-term decline in human population numbers. The real question then becomes not did Toba almost kill us, but rather, how did we survive a world where Toba was just one more challenge added to an already difficult environment? And to answer that question, we need to look at the people themselves. Who were these early humans? Where were they living? And what tools, both literal and metaphorical, did they have at their disposal? But before we meet our ancestors face to face, we need to understand how scientists have pieced together this story, because the evidence for human survival doesn't come from written records or even from complete skeletons. It comes from some of the most subtle and hard-won clues imaginable: microscopic fragments of volcanic glass and the careful study of ancient stone tools. This is detective work on a planetary scale, and it's revolutionized our understanding of what happened 74,000 years ago. Chapter 4: The Evidence Trail, Following Microscopic Clues Across Continents. When Gene Smith, a geologist studying volcanic eruptions, first proposed looking for microscopic volcanic glass in African archaeological sites in the early 2000s, many of his colleagues were skeptical. The idea seemed almost absurd on its face. Here was a proposal to search for particles smaller than the width of a human hair, particles so tiny they'd be invisible to the naked eye, particles scattered across an entire continent, buried in sediments that had been sitting in the ground for 74,000 years. The chances of finding them, let alone finding enough to make meaningful scientific inferences, seemed vanishingly small. But Smith understood something crucial about how supervolcanoes work, something that would revolutionize our understanding of the Toba eruption and its global impacts. He knew that when these monsters erupt, they don't just produce the chunky pumice stones and visible ash that fall close to the volcano. They also produce what volcanologists call cryptotephra, from the Greek words for hidden ash. Cryptotephra consists of ultrafine particles of volcanic glass, shards so small that thousands of them could fit on the head of a pin. These particles are created in the most violent phase of the eruption, when superheated magma explodes into the atmosphere and cools so quickly that it doesn't have time to form crystals. Instead, it freezes into glass, shattering into microscopic fragments that can be carried enormous distances by high-altitude winds in the stratosphere. The beauty of volcanic glass, from a scientific perspective, is that it preserves the chemical signature of the magma it came from. Different volcanoes around the world produce magmas with different chemical compositions, different ratios of silicon to iron, different amounts of titanium or aluminum or potassium. These ratios act like a fingerprint. If you can measure the chemistry of a tiny shard of volcanic glass precisely enough, you can match it to specific eruptions. This means that cryptotephra scattered from a super eruption like Toba creates a time marker, what geologists call an isochronous horizon, a single moment in time frozen into rock layers across vast geographical areas. Every site where you find Toba glass, you know you're looking at sediments that were deposited right around 74,000 years ago. And if those sediments also contain evidence of human occupation, you can divide that occupation into before Toba and after Toba with extraordinary precision. The process of actually finding and identifying cryptotephra is painstakingly slow and requires almost monastic patience. It begins in the field, at archaeological sites where researchers are carefully excavating layers of sediment that have accumulated over thousands or tens of thousands of years. Every layer, every thin band of soil or sand or clay, represents a slice of time. And somewhere in that sequence, if the site is old enough and in the right geographical area, there might be a layer containing Toba glass. Researchers collect samples systematically, documenting exactly which layer each sample comes from, measuring its depth below the surface, noting any archaeological materials like stone tools or animal bones found nearby. These samples are carefully packaged and transported back to the laboratory, where the real detective work begins. In the lab, the sediment samples go through a series of processing steps designed to concentrate any volcanic glass particles they might contain. First, organic material is dissolved away using chemical treatments. Then the sample is washed through increasingly fine sieves to separate particles by size. Volcanic glass from supereruptions tends to fall within a particular size range, typically between 20 and 50 microns. For reference, a human hair is about 100 microns in diameter, so we're talking about particles that are half the width of a hair or smaller. Once the sample has been concentrated down to particles in the right size range, the real challenge begins. Under a microscope, a researcher must visually scan through thousands of particles, looking for ones that have the characteristic appearance of volcanic glass. This requires a trained eye, because volcanic glass particles look similar to other natural materials, like quartz grains or tiny mineral crystals. Potential glass particles are picked out one by one using a micromanipulator, an instrument that combines a microscope with tiny mechanical or electronic arms capable of moving with precision measured in microns. Imagine trying to pick up individual grains of sand with chopsticks. Then imagine those grains are 10 times smaller than sand, and you'll have some sense of the delicacy required. Each particle that looks promising is then mounted on a stub for analysis using an electron microscope. Unlike optical microscopes that use visible light, electron microscopes use beams of electrons to image materials at much higher magnifications. More importantly for this research, electron microscopes can be equipped with detectors that measure the X-rays emitted when the electron beam hits the sample. Different chemical elements emit X-rays at characteristic energies, so by analyzing these X-rays, researchers can determine the exact chemical composition of the particle. This is where the volcanic fingerprint comes in. The chemical composition of Toba glass is well known from studies of the ash deposits near the volcano itself. It has specific ratios of major elements like silicon, aluminum, iron, magnesium, calcium, sodium, and potassium. When a particle found in an African archaeological site matches this Toba fingerprint, you know with high confidence that it travelled from Sumatra to Africa 74,000 years ago. The first successful identification of Toba cryptotephra in Africa was a triumph, a proof that Smith's seemingly quixotic quest was actually feasible. In sediments from Lake Malawi in East Africa, approximately 7,000 kilometers from the volcano, researchers found particles whose chemistry matched Toba perfectly. The glass had made an incredible journey, lofted into the stratosphere by the eruption's violent column, carried westward by high-altitude winds, gradually settling through the atmosphere over weeks or months, finally coming to rest in the sediments of an East African lake. But finding glass in a lake sediment core, while scientifically valuable for understanding the eruption's reach and environmental impacts, wasn't quite the Holy Grail. What researchers really wanted was to find Toba glass in archaeological sites, places where humans were living at the time of the eruption, because only then could you see whether human behavior changed in response to the catastrophe. At Pinnacle Point on the southern coast of South Africa, a series of caves overlooks what is now the Indian Ocean. These caves have been occupied on and off by humans for tens of thousands of years, and they contain one of the most complete archaeological records of Middle Stone Age human behavior anywhere in Africa. The sediments in these caves are like a time capsule, preserving not just stone tools but also the bones of animals that were hunted and eaten, remnants of ancient hearths where fires burned, and even microscopic traces of plant material and ochre used for symbolic purposes. When researchers began looking for Toba cryptotephra at Pinnacle Point, they knew they were in the right time period. The layers they were interested in dated to around 74,000 years ago based on other dating techniques. But finding the actual glass required processing hundreds of samples, scanning through millions of particles under the microscope, picking out thousands of candidates for electron microscopy analysis. The work took years, but eventually, success. In sediments dating to right around 74,000 years ago, scattered among the normal sediment particles, they found shards of volcanic glass with the unmistakable Toba chemical signature. The eruption's fallout had reached even here, to the southern tip of Africa, almost as far from Sumatra as you can get on Earth's surface without crossing an ocean. But finding the glass was only the beginning. What really mattered was what was found alongside it, what the archaeology above and below the Toba layer could tell us about how people responded. The stone tools found in layers below the Toba glass versus those above it showed remarkable continuity. The people at Pinnacle Point were making what archaeologists call still bay points, sophisticated stone projectile points that required considerable skill to manufacture. These points have a distinctive shape, carefully thinned on both sides to create sharp cutting edges with a broad base that could be attached to a wooden or bone shaft. The still bay tradition, named after the type site where these tools were first recognized, represents one of the most advanced stone tool technologies of the Middle Stone Age. Making these points required not just technical skill but also planning and foresight. The toolmaker had to select the right kind of raw material, had to understand how stone fractures under different conditions, had to execute a carefully planned sequence of flaking operations to achieve the desired shape. A single mistake could ruin hours of work. What the Pinnacle Point researchers found was that this technological tradition continued uninterrupted across the Toba event. The same types of points, made using the same techniques, appear in layers before and after the glass layer. There's no dramatic break, no sign that the people living at the site disappeared or were replaced by others, no indication that their culture collapsed. In fact, in some of the layers dating to shortly after Toba, there's evidence of increased technological sophistication. The points become slightly more refined, with better pressure flaking along the edges. New tool types appear, including small-backed pieces that might have been used as components of composite tools, where multiple small stone pieces are set into a handle with adhesive. There's also increased use of heat treatment, a sophisticated technique where stone raw materials are carefully heated to specific temperatures to improve their flaking properties. Heat treatment can transform mediocre quality stone into excellent toolmaking material, and it requires considerable knowledge to do properly. Heat it too little and nothing happens. Heat it too much and the stone crumbles. The use of ochre, iron-rich minerals ground into powder and used for various purposes including body decoration, also continues and perhaps intensifies after Toba. Pieces of ochre with grinding facets, showing they were rubbed against rough surfaces to produce powder, are found throughout the sequence. Beyond the tools themselves, the faunal remains, the bones of animals that were hunted and eaten, show continuity in subsistence strategies. People were hunting a mix of large and small game, from dangerous prey like buffalo and warthogs to smaller, less risky targets like tortoises and hyraxes. They were also exploiting marine resources, collecting shellfish from the rocky shores below the caves. This pattern of resource use doesn't change dramatically across the Toba event. There's no sudden shift to only eating small game or an abandonment of shellfish collecting. Life, in terms of daily subsistence activities, seems to have continued much as before. Now, it's important to note what this evidence doesn't show. It doesn't prove that the people at Pinnacle Point were unaffected by Toba. It's possible that population sizes declined, that times were harder, that people were stressed in ways that don't leave obvious archaeological traces. But what it does show clearly is that people didn't disappear. They didn't abandon the site. Their culture and technology didn't collapse. They endured. Similar stories emerged from other sites. At Mossel Bay, also in South Africa, human occupation continued across the Toba period. At Blombos Cave, famous for its evidence of early symbolic behaviour, including engraved ochre and shell beads, there's no sign of disruption around 74,000 years ago. In East Africa, the picture is similar. At sites in Kenya and Tanzania, where Toba cryptotephra has been found in sediments of the right age, archaeological evidence shows continuity rather than catastrophe. At Enkapune ya Muto in Kenya, a rock shelter with a long sequence of Middle Stone Age occupation, there's no break in the sequence around the time of Toba. But perhaps the most detailed picture of human survival during the Toba period comes from Ethiopia, from a site called Shinfa Metama, 1 inch the lowlands of northwestern Ethiopia, near the modern border with Sudan. This site has provided some of the most compelling evidence for how humans not just survived, but actually adapted and thrived in the face of environmental challenges posed by Toba. Shinfa Metama 1 is located in what is now a somewhat arid region, but 74,000 years ago it sat near an ancient river system, part of the Blue Nile watershed. The site is not easy to access or work in. It's hot, remote, and during certain seasons, plagued by biting insects. But these challenges have been more than worth it for the insights the site has provided. The excavations at Shinfa Metama 1, led by John Kappelman of the University of Texas at Austin and his colleagues, uncovered something remarkable. Not just Toba cryptotephra, though they found that too, but actual visible Toba ash. In some layers, you could see the ash with the naked eye, a grey-white band in the reddish-brown sediments. The eruption had deposited enough material this far from the volcano that it left a distinct marker you didn't need a microscope to see. And around that ash layer, both above and below it, the researchers found abundant evidence of human activity. Stone tools were scattered throughout the deposits, including both small, carefully made projectile points and larger cutting and scraping tools. The points were particularly interesting because their small size and shape suggested they might have been arrow points rather than spear points, potentially indicating the use of bow and arrow technology. If this interpretation is correct, and it remains debated, it would represent a major technological innovation. Bow and arrow hunting is significantly more effective than spear hunting because it allows striking from much greater distances, requires less physical strength, and gives the hunter multiple attempts at a target. The development of this technology during the stressful period around Toba would be exactly the kind of innovation under pressure that some researchers have suggested characterized human responses to environmental challenges. But it wasn't just stone tools that the Shinfa Metama excavators found. They also uncovered large numbers of animal bones, including remains of various mammals that would have been hunted for food, and intriguingly, they found substantial numbers of fish bones, especially in the layers dating to around and after the Toba eruption. The fish were a surprise. Most Middle Stone Age archaeological sites in Africa contain few, if any, fish bones. Fishing doesn't seem to have been a major part of the subsistence strategy for most human populations at this time. The fact that fish suddenly become much more common in the Shinfa Metama deposits right around the time of Toba suggested something important was going on. To understand what that something might be, the research team did something clever. They analysed the chemical composition of fossil ostrich eggshells and mammal teeth found in the same layers as the human artifacts. Specifically, they measured oxygen and carbon isotopes in these materials. Isotopes are variants of chemical elements that have different numbers of neutrons in their nuclei. Oxygen, for example, comes in several isotopes, including oxygen 1,6 and oxygen 1,8. These isotopes behave almost identically in chemical reactions, but they have slightly different masses, which means they respond slightly differently to physical processes like evaporation. When water evaporates from the ocean, the lighter oxygen 1,6 evaporates preferentially, leaving the ocean slightly enriched in the heavier oxygen 1,8. When that water vapor falls as rain over land, the heavier isotope tends to fall out first. This means that rain falling far from the ocean, or falling from air masses that have already dumped a lot of rain elsewhere, will be isotopically different from rain falling near the coast. Animals drinking water from different sources, or eating plants that grew using different water sources, will incorporate those isotopic signatures into their bodies, specifically into their tooth enamel and eggshells, which preserve these chemical signals long after the animal has died. By measuring the oxygen isotope ratios in ostrich eggshells and mammal teeth from Shinfametama, the researchers could reconstruct something about the precipitation patterns and water availability in the region at different times. And what they found was striking. Before Toba, the isotope ratios suggested relatively moist conditions, with regular rainfall and reliable water sources. But after Toba, the ratios shifted toward values indicating more arid conditions. The monsoon rains that had watered the region were weakening. The climate was becoming drier. Carbon isotopes told a complementary story. Different types of plants, specifically trees and shrubs versus grasses, incorporate carbon isotopes in slightly different ways due to differences in their photosynthesis mechanisms. By analyzing carbon isotopes in the tooth enamel of herbivores, researchers can tell what proportion of their diet came from trees and shrubs versus grasses. At Shinfametama, the carbon isotope data showed a shift toward more grass eating after Toba, suggesting that the landscape was opening up, with grasslands replacing some of the tree and shrub vegetation that had been more prominent before. So the picture that emerged was one of increasing aridity, of a landscape becoming more open and dry, and in this changing environment, fish became increasingly important to the human occupants of the site. Why fish? The answer lies in understanding how rivers behave in seasonal environments. During the wet season, rivers flood, spreading across wide floodplains, creating an abundance of aquatic habitats. But during the dry season, rivers contract, sometimes breaking up into a series of isolated pools or waterholes as the water level drops. In increasingly arid conditions, this seasonal variation would have become more extreme. Dry seasons would be longer and more severe. Rivers would contract more dramatically. But those remaining waterholes would have become crucial resources, concentrating not just fish but also other animals that needed to drink. The research team proposed that the humans at Shinfametama were practicing what they called a hydro-refugia strategy. During the dry season, when resources were scarce elsewhere, they were following the river system, moving from waterhole to waterhole. At each stop, they would exploit the resources available, which increasingly included fish from the contracting river. This kind of behavioral flexibility, this ability to adjust subsistence strategies in response to changing environmental conditions, might have been key to survival during the Toba period and the broader climate instability of which Toba was a part. The pattern of stone tools and other artifacts at the site supported this interpretation. Rather than being concentrated in one area, suggesting permanent occupation, the artifacts were scattered along what would have been the ancient river course, suggesting a pattern of repeated short-term occupations at different points along the river. People were moving, following the water and the resources it provided. This mobility itself was an adaptive strategy. Rather than trying to stay in one place as conditions deteriorated, the people at Shinfametama were ranging widely, exploiting different resource patches as they became available, never staying anywhere long enough to completely deplete local resources. Archaeological evidence from India adds another dimension to our understanding of human survival during Toba. India is particularly important for this story because it's closer to the volcano, and indeed, some parts of India received massive ash falls. The younger Toba tuff, as the ash layer is called, reaches thicknesses of 3 meters or more in parts of central India. This is visible ash, layers you can see without any instruments, blankets of volcanic debris that must have had immediate and dramatic effects on local environments. At a site called Jwalapuram in the Jururu Valley of southern India, archaeologists found what initially seemed like it should be the smoking gun evidence for catastrophic effects of Toba on human populations. The site contains a thick layer of ash, several meters deep in places, clearly from the Toba eruption based on its chemistry and age. Surely, you'd think, this would be a place where humans disappeared, where the archaeological record showed a dramatic break. But that's not what researchers found. When they excavated both below and above the ash layer, they found Middle Paleolithic stone tools in both contexts. The tools above the ash looked essentially identical to those below it. The same technological tradition, the same basic patterns of tool manufacture, the same types of raw materials being used. The idea seemed almost absurd, trying to find particles smaller than the width of a human hair in sediments that had been sitting in the ground for 74,000 years, scattered across a continent thousands of miles from the volcano. But Smith understood something crucial. When supervolcanoes erupt, they don't just produce the large chunks of pumice and ash that fall close to the volcano. They also produce cryptotephra, ultra-fine particles of volcanic glass that can be carried enormous distances by high-altitude winds. These particles are tiny, typically 20 to 50 microns across. To give you a sense of scale, a human hair is about 100 microns in diameter. So we're talking about particles that would appear as mere specks, even under a microscope. But they have 3 crucial properties that make them invaluable to scientists. First, volcanic glass has a unique chemical composition that acts like a fingerprint. Different volcanoes produce glass with different ratios of elements like silicon, titanium, aluminum, and iron. By analyzing these ratios, scientists can match glass particles to specific eruptions. Second, volcanic glass is remarkably durable. Unlike organic materials that decay or minerals that can be dissolved by groundwater, glass can persist essentially unchanged for millions of years. Third, and most importantly, when cryptotephra from a massive eruption like Toba settles across a wide area, it creates a time marker, a single moment frozen in the geological record. Every site where you find Toba glass, you know you're looking at a layer that was deposited around 74,000 years ago. This last property is what makes cryptotephra so powerful for understanding human history. If you can find Toba glass in an archaeological site, you can divide that site's history into before Toba and after Toba, allowing you to see whether human behavior or occupation changed after the eruption. The process of finding and identifying cryptotephra is painstakingly slow. Researchers take sediment samples from archaeological sites, carefully noting exactly which layer each sample comes from. Back in the lab, they process these samples to separate out any particles that might be volcanic glass. This involves using chemicals to dissolve away organic material and minerals, followed by careful sieving to concentrate particles of the right size range. Then comes the really delicate work, using an instrument called a micromanipulator, essentially a microscope with tiny robotic arms. Researchers pick out individual particles that look like they might be glass. These particles are then analyzed using an electron microscope, which can determine their chemical composition with extraordinary precision. It took years of patient work, but eventually Smith and his colleagues found what they were looking for. In sites across East Africa, from Ethiopia to South Africa, they discovered particles whose chemical composition matched Toba exactly. The glass had travelled over 7,000 kilometers, carried by winds in the stratosphere, and had fallen like an invisible snow across the continent. But finding the glass was only the beginning. What really mattered was what was found alongside it. At Pinnacle Point on the southern coast of South Africa, researchers found Toba cryptotephra in sediments associated with Middle Stone Age human occupation. The site is a series of caves overlooking what is now the Indian Ocean, and it contains one of the most complete archaeological records of human behavior spanning the period around Toba. When the team examined the stone tools and other artifacts found in layers below the Toba glass versus those above it, they found remarkable continuity. The same types of sophisticated stone points, evidence of ochre use for symbolic purposes, the same patterns of resource exploitation. There was no dramatic break, no sign that the people living at Pinnacle Point had been decimated by the eruption. In fact, some evidence suggested the opposite. In the layers dating to shortly after Toba, researchers found increased technological sophistication in stone tool manufacture, new techniques for working stone that produced more efficient tools. Rather than a population struggling to survive, this looked like a population adapting and innovating. Similar discoveries were made at other sites. At Mossel Bay, also in South Africa, human occupation continued across the Toba event. At sites in Kenya and Tanzania, the same pattern emerged, evidence of continuity rather than catastrophe. But it was in Ethiopia, at a site called Shinfa Metama 1, that perhaps the most detailed picture emerged. Shinfa Metama 1 is located in the lowlands of northwestern Ethiopia, near the modern border with Sudan. It's not exactly an easy place to work. The site is remote, hot, and during certain seasons, plagued by insects. But its location turns out to be exactly what makes it so valuable for understanding human survival of Toba. The site sits near an ancient river system, part of the Blue Nile watershed. When researchers began excavating here, they knew they were looking at Middle Stone Age deposits, but they didn't initially realize just how special the site was. Then they found the ash, not cryptotephra this time, but actual visible Toba ash, a layer they could see without a microscope. The eruption had deposited enough material this far from the volcano that it left a distinct band in the sediments, and around that ash layer, above and below it, they found abundant evidence of human activity. Stone tools, animal bones from hunting and scavenging, evidence of fire use, and most intriguingly, fish remains. The fish were particularly interesting because they suggested something important about how people were surviving in this environment. Most Middle Stone Age sites in Africa contain few, if any, fish bones. Fishing, it seems, wasn't a common strategy for most human populations at this time, but at Shinfa Metama 1, fish were abundant, especially in the layers dating to around and after the Toba eruption. The researchers realized they were looking at evidence of adaptive behavior, people adjusting their subsistence strategies in response to environmental stress. The team did something clever to understand the environmental conditions at the site. They analyzed oxygen and carbon isotopes from ostrich eggshells and from the teeth of fossil mammals found in the same layers as the human artifacts. These isotopes act as a kind of thermometer and rain gauge, preserving information about temperature and precipitation from the time the animals were alive. What they found was that the environment around Shinfa Metama 1 had been relatively moist before Toba, but became significantly more arid afterward. The monsoon rains that had watered the region weakened. The landscape shifted toward more open, drier conditions. In such conditions, large game would have become harder to find. Plants that humans relied on might have become scarcer, but the river remained, and with it, a reliable source of protein in the form of fish. The researchers also found evidence of what they called hydrorefugia behavior. During the dry season, which would have become more pronounced after Toba, the river would have contracted into a series of waterholes. These waterholes would have been crucial resources, attracting both animals and humans. The pattern of stone tools and other artifacts suggested that people were moving along the river system, perhaps following it upstream during dry seasons to find fresh water. This kind of behavioral flexibility, this ability to adjust subsistence strategies and movement patterns in response to changing conditions, might have been key to human survival, not just of Toba, but of the broader environmental challenges of this period. Another crucial piece of evidence came from India, where the debate over Toba's impact has been particularly intense. At a site called Jwalapuram in the Jureru Valley of southern India, archaeologists found something remarkable. The site contains a thick layer of Toba ash, in some places more than 3 meters deep. This is ash you can see without any special instruments, a clear marker that this area was heavily affected by the eruption. Surely, if Toba had catastrophic effects on human populations, this would be the place to see it. But when the researchers excavated both below and above the ash layer, they found Middle Paleolithic stone tools in both contexts. The tools above the ash looked essentially identical to those below it. The same technological tradition, the same basic patterns of tool manufacture. There was no evidence of a break in human occupation. A 2020 study at another Indian site, Darba in the Middle Sun Valley, found similar results. The site contained an 80,000-year-long stratigraphic sequence, and stone tools were found in layers spanning from well before Toba to well after. The tools showed clear continuity across the Toba event. Now, skeptics have pointed out that the dating at some of these Indian sites is not as precise as we'd like, and that there could be gaps in the sequence that aren't immediately obvious. It's always possible that people abandoned the area for a while after Toba and then returned later. But the cumulative evidence from multiple sites across multiple continents is building a compelling case that human populations were more resilient, more widespread, and more adaptable than the original catastrophe theory suggested. Perhaps the most remarkable discovery has come from the last few years. As genetic techniques have become more sophisticated, researchers can now extract and sequence DNA from ancient human remains, allowing them to directly examine the genetic makeup of people who lived tens of thousands of years ago. In 2019, a team analyzed the genome of a 45,000-year-old modern human from Siberia. By comparing this ancient DNA to the genomes of people alive today, they could trace the history of human populations with unprecedented detail. What they found was that yes, human populations did go through bottlenecks, periods when population sizes crashed, but the timing and severity of these bottlenecks varied by region. Some populations crashed hard, others less so, and critically, the bottlenecks don't all line up perfectly with 74,000 years ago. In fact, for many African populations, the evidence suggests the bottleneck occurred slightly earlier, perhaps around 70 to 80,000 years ago. For non-African populations, the severe bottleneck associated with the dispersal out of Africa happened a bit later, around 50 to 60,000 years ago. The picture that's emerging is more complex than a single catastrophic event causing a single bottleneck. Instead, we're seeing evidence of multiple factors at play. Climate instability, yes, but also the structure of human populations, which were probably organized into many small, semi-isolated groups spread across Africa and parts of Asia. Toba may have contributed to population declines, may have exacerbated stress on human groups, may have influenced which groups survived and which didn't, but it wasn't the sole cause. It was one factor among many. This doesn't diminish the eruption's importance. An event that injected hundreds of millions of tons of sulfur into the stratosphere, that caused global cooling, that deposited ash across 2 continents, that nearly coincided with one of the more severe climate deteriorations of the last 100,000 years, that's still a major player in human evolutionary history. What's changed is our appreciation for human resilience, for the ability of our ancestors to adapt, to innovate, to find ways to survive, even when the odds seemed overwhelming. So who exactly were these survivors? What were they like? These people who lived through one of the planet's most catastrophic events. Chapter 5. Human populations before Toba. 74,000 years ago, the world was a very different place, and so were we. If you could travel back in time to that period, you would find Homo sapiens, anatomically modern humans, living primarily in Africa, with some populations having already dispersed into parts of Asia, and perhaps even reaching as far as Australia. But you would also encounter other human species. Neanderthals were thriving across Europe and Western Asia. Denisovans, a sister species to Neanderthals known mainly from their DNA, inhabited parts of Siberia and Eastern Asia, and in isolated pockets, other archaic human populations might have still existed, the last holdouts of species like Homo erectus that had once been widespread. This was a time when humanity was plural, when multiple human species shared the planet, and all of them were about to face the Toba challenge. But let's focus on our own direct ancestors, the Homo sapiens populations that would eventually give rise to every human alive today. In Africa, which was still home to the vast majority of the human population, our ancestors lived in small, mobile bands probably numbering between 30 and 100 individuals. These weren't primitive people by any stretch. The term Stone Age can be misleading, suggesting a simplicity that wasn't there. The humans of 74,000 years ago had brains just as large and complex as ours. They had language, almost certainly. They had culture, traditions passed down from generation to generation. They had art, as evidenced by ochre-engraved patterns found at sites like Blombos Cave in South Africa dating to this period. They had complex social structures, with kinship networks that extended beyond their immediate band. They had spirituality, though we can only guess at its exact nature based on the hints they left behind. Careful burials, the use of pigments, the crafting of objects that seem to have no practical purpose beyond the symbolic. Technologically, they were sophisticated. The stone tools found at sites dating to this period show remarkable skill. These aren't just rocks that have been bashed against other rocks until they break in a useful way. They're carefully planned and executed pieces of technology. The process of creating a Middle Stone Age stone point began with selecting the right kind of raw material, usually a fine-grained stone like flint, chert, or obsidian. The toolmaker would then carefully strike flakes off a larger core stone, controlling the angle and force of each blow to produce flakes of a specific size and shape. These flakes would then be further refined, a process called retouching, where tiny chips are removed from the edges to create a sharp, durable cutting edge, or to thin the piece so it can be mounted on a handle. The result is a tool that can last for years with periodic resharpening, something that can be used to butcher animals, to scrape hides, to shape wood or bone. But these people had more than just stone tools. They made use of bone and wood, though these materials rarely survive in the archaeological record. They created cordage from plant fibers, which they could use to make nets or to attach stone points to spears. They knew which plants were edible, which had medicinal properties, which could be used for crafting or for fire starting. They understood animal behavior intimately. They knew the seasonal movements of herds, the watering holes where prey would gather, the signs that indicated a successful hunt versus one that would be futile. This knowledge was cumulative, passed down through generations, refined and added to over centuries. And they had fire, not just as something they could keep going if they found a natural source, but as something they could create at will. The ability to make fire on demand was transformative. It meant warmth in cold climates. It meant protection from predators. It meant the ability to cook food, which made nutrients more accessible and reduced the time needed for digestion. Fire also meant light after dark, extending the hours when work could be done or stories could be told. It meant a focal point for the band, a place where people gathered, where social bonds were reinforced, where knowledge was transmitted from old to young. The populations that would face Toba were probably organized into a network of bands spread across the African continent, with some groups having already moved into the Middle East and South Asia. Genetic evidence suggests there was gene flow between groups, occasional interbreeding that prevented populations from becoming too isolated, but at the same time, each band probably had its own territory, its own traditions, its own subtle variations in language and culture. The total human population at this time was probably somewhere between a few 100,000 and perhaps 1 million individuals worldwide. This might sound like a lot, but spread across 3 continents, it meant that human population density was incredibly low. You could walk for days, perhaps weeks, without encountering another human band. This low population density had its advantages and disadvantages. On one hand, it meant that epidemic diseases, which required dense populations to sustain themselves, were probably rare. On the other hand, it meant that when environmental conditions deteriorated, When droughts struck or game became scarce, there weren't a lot of options for getting help from neighbours or moving to more favourable areas. The environment our ancestors inhabited before Toba varied widely. Some groups lived in coastal areas, exploiting marine resources like shellfish. Others lived in river valleys, following waterways that provided reliable access to fresh water and attracted game. Still others adapted to more arid environments, learning to find water in unlikely places and to make use of the scattered resources these harsh landscapes provided. But wherever they lived, all of them were subject to the climate's whims. The period around 74,000 years ago was already climatically unstable. The world was in a transitional phase, sliding from the relative warmth of an interglacial period into the deeper cold of a glacial phase. This meant that conditions were already changing, already challenging. Rainfall patterns were shifting. Some areas that had been relatively wet were becoming drier. Ice sheets in the northern hemisphere were beginning to expand, locking up water and lowering sea levels, creating new coastal plains but also disrupting ocean circulation patterns. Our ancestors had already been adapting to these changes, probably for generations. They would have seen the herds their grandparents hunted become scarcer or move to different areas. They would have seen familiar waterholes dry up, forcing them to range farther in search of water. They would have developed strategies for coping with variability, for planning ahead, for storing food when it was abundant to get through lean times. All of these adaptations, all of this cultural and technological sophistication would be put to the test when Toba erupted. But perhaps, paradoxically, it was because conditions were already challenging that humans were able to survive what came next. A species that had grown comfortable, that had specialized too narrowly for a particular environment, might have been wiped out by Toba's effects. But a species that was already adaptable, already accustomed to dealing with change, that had the cognitive flexibility and the technological toolkit to adjust to new challenges, that species had a chance. Chapter 6. Survival Strategies. When the skies darkened and the ash began to fall, our ancestors didn't have the luxury of understanding what was happening in scientific terms. They didn't know about volcanoes or sulfate aerosols or volcanic winter. They only knew that their world was changing, and they had to respond. The question is, how? The archaeological evidence gives us tantalizing clues, but we have to be careful about over-interpreting. We're looking at scattered snapshots of behavior from 74,000 years ago, preserved in the archaeological record more by luck than anything else. Still, some patterns emerge. The first and perhaps most important survival strategy was one our ancestors had been practicing for hundreds of thousands of years: mobility. Humans are one of the most mobile species on the planet, capable of covering large distances on foot and, crucially, capable of adapting to new environments quickly. When conditions in one area became untenable, the response was often to move. And while we can't track individual bands across the landscape 74,000 years ago, we can see evidence of human presence in an increasingly wide range of environments during this period. This flexibility is actually visible in the archaeological record. Stone tools from this period show that people were exploiting resources from multiple environments. At coastal sites, we find shells from marine mollusks. At inland sites, we find bones from terrestrial game. At sites near rivers or lakes, we find fish bones. The key is that people weren't specializing narrowly. They were generalists, able to switch between different food sources as circumstances demanded. When large game became scarce, they turned to smaller animals. When hunting was poor, they relied more heavily on gathered plant foods. When neither hunting nor gathering provided enough, they turned to fishing or collecting shellfish. This kind of dietary flexibility requires knowledge. You need to know which plants are edible and when they fruit. You need to know where to find shellfish and how to open them efficiently. You need to know how to fish, which requires either making hooks or constructing traps or weirs. The archaeological evidence from Shinfa Metama, 1-inch Ethiopia, provides a concrete example. Before Toba, fish bones are relatively rare at the site. After Toba, they become much more common. This suggests that as conditions became more arid, as large game perhaps became harder to find, people adjusted by exploiting the river more intensively. This kind of shift requires not just knowledge, but also the willingness to change behavior, to try new strategies even if they're unfamiliar. It's a kind of cognitive flexibility that's easy to take for granted but is actually quite remarkable. Another survival strategy that appears in the archaeological record is technological innovation. At Pinnacle Point in South Africa, researchers found evidence that people began producing more sophisticated stone tools in the aftermath of Toba. Specifically, they began using a technique called pressure flaking more frequently. Pressure flaking is a method of shaping stone tools by pressing against the edge with a pointed tool, often made of bone or antler, rather than striking it. This technique allows for much finer control over the shape of the tool, producing thinner, sharper implements. These tools are more efficient, cutting better, and lasting longer between resharpenings. Why would people start using this more sophisticated technique after Toba? One possibility is that as resources became scarcer, there was increased selective pressure to make every hunt count. A sharper, more reliable spear point might mean the difference between a successful hunt and going hungry. Another possibility is that as populations were stressed, the most skilled toolmakers, the individuals who could produce the best tools, had a survival advantage. Their knowledge would have been valuable to their bands, increasing their status and ensuring they were well supported by the group. But technology wasn't just about better tools, it was also about new tools. At several sites dating to around the time of Toba, we see the first evidence of specialized tools for specific tasks. Scrapers designed for working hides, drilling tools for making holes in shells or bones, and possibly even the earliest evidence for projectile weapons more advanced than simple throwing spears. The appearance of bow and arrow technology is particularly interesting. Some of the stone points found at sites like Shinfa Metama, one are small enough and shaped in a way that suggests they were used as arrow points rather than spear points. If true, this would represent a major technological advance. Bow and arrow hunting is significantly more effective than spear hunting for several reasons. First, it allows you to strike from a much greater distance, reducing the chance that your prey will detect you and flee. Second, it requires less physical strength to use, meaning that more members of the band, including younger individuals and women, could participate in hunting. Third, it's much easier to carry multiple arrows than multiple spears, giving you more chances for a successful hit. The archaeological evidence isn't conclusive, but the size and shape of some Middle Stone Age points are consistent with arrow use. And if our ancestors did develop this technology during the stressful period around Toba, it would represent exactly the kind of innovation that could improve survival odds. Beyond technological strategies, there were also social and organizational changes. The genetic evidence, while complex, suggests that human populations during this period were structured in a particular way. Rather than one large, interconnected population, humans lived in many small, semi-isolated groups with occasional gene flow between them. This structure, sometimes called metapopulation dynamics, actually provides some resilience to catastrophic events. If conditions in one area become untenable and a local population goes extinct, other populations survive elsewhere. And eventually, if conditions improve, those surviving populations can expand and recolonize the areas that were abandoned. There's also evidence that our ancestors practiced what anthropologists call risk buffering through social networks. Even though individual bands were small and mobile, they maintained connections with other bands in the region. These connections were reinforced through occasional meetings, through the exchange of gifts, and through marriages that created kinship ties across bands. These networks meant that in times of stress, a band in trouble could potentially seek help from or join up with allied bands. A group facing starvation might be able to rely on gifts of food from better-off neighbors, with the understanding that the favor would be returned if circumstances reversed. We can't see these social networks directly in the archaeological record, but we can see hints of them in the distribution of certain materials. For example, shell beads found hundreds of kilometers from the nearest coast or high-quality stone from a known outcrop found at sites far away. These patterns suggest that materials, and probably people, were moving across the landscape, maintaining connections despite distances. Fire use also became even more critical during periods of environmental stress. Fire provided not just warmth, but also a way to make certain foods edible that would otherwise be indigestible. Many tubers and roots that are toxic when raw become safe to eat after cooking. In a world where food was becoming scarcer, the ability to exploit these previously unusable resources could make the difference between survival and starvation. Fire could also be used to manage landscapes. Controlled burning of grasslands can promote the growth of certain plant species, making those areas more attractive to grazing animals. There's evidence from other periods that humans used fire this way, essentially creating better hunting grounds. It's possible, though not proven, that our ancestors practiced this during the Toba period as well. Perhaps one of the most important survival strategies was simply knowledge itself. The bands that survived Toba were probably those that had the deepest knowledge of their local environments, the ones that knew where to find water even in the driest seasons, that knew which plants could be eaten when others failed, that could read the subtle signs in animal behavior that indicated where game might be found. This knowledge was transmitted culturally, taught by older, experienced members of the band to younger ones. The value of having elders who remembered previous droughts, who had lived through hard times before and knew how to cope, would have been immeasurable. In this light, the survival of humanity through Toba becomes less about any single strategy and more about the total package of human adaptability. Our mobility, our cognitive flexibility, our technological sophistication, our social networks, our ability to accumulate and transmit knowledge across generations. None of these traits was unique to humans. Neanderthals had many of the same capabilities. Denisovans presumably did too, but the combination, along with a bit of luck in terms of where populations happened to be located when Toba erupted, was enough to allow some human groups to endure. And it's worth noting that we don't know that all human groups did survive. The genetic evidence suggests severe bottlenecks, which means many populations probably did go extinct. The humans that survived were probably not uniformly distributed across the landscape, but concentrated in certain favourable areas, what biologists call refugia. These refugia would have been places where conditions remained tolerable, even as they deteriorated elsewhere. Coastal areas might have qualified, since the ocean would have moderated temperature extremes and provided reliable food sources. River valleys in Africa might have served as refugia, maintaining some moisture even as surrounding areas became arid. In these refugia, human populations might have contracted, becoming more concentrated. This would have made it easier to maintain social connections, to share knowledge, to support each other through difficult times. And when conditions eventually improved, these surviving populations would have been poised to expand outward again, recolonizing areas that had been abandoned. The story of human survival through Toba is ultimately a story about our species' defining characteristic, not our intelligence per se, but our adaptability, our ability to face unprecedented challenges and find ways, however imperfect, to cope. Chapter 7. The Genetic Legacy. If you could somehow extract a single cell from your body right now, perhaps a cheek swab, and sequence its DNA, you would find written there, in the language of genetic code, the echo of Toba. The evidence is subtle, requiring sophisticated analysis to detect, but it's there. In the pattern of mutations across your genome, in the relationships between different versions of genes, in the overall level of genetic diversity that characterizes our species, we can read the history of population expansions and contractions, of migrations and isolations, of bottlenecks and founder effects. And one of those signals points to a severe population contraction roughly 70,000 years ago, right around the time of Toba. Let's talk about what genetic bottlenecks actually mean and how we detect them. Every gene in your body exists in multiple versions called alleles. For example, the gene that determines your blood type comes in 3 main alleles, A, B, and O. The combination of alleles you inherited from your parents determines your blood type. Now, In a large population that's been stable for a long time, you'll find lots of genetic diversity. There will be many different alleles for each gene, representing mutations that arose at various points in the past and have been maintained in the population. Some alleles will be common, others rare, but overall there's a lot of variation. But when a population goes through a bottleneck, when numbers crash to a small fraction of what they were before, something interesting happens. Rare alleles are often lost entirely, simply by chance. If only a few individuals survive, and they happen not to carry the rare version of a gene, that allele disappears from the population forever. Even common alleles can be lost, and the overall effect is a dramatic reduction in genetic diversity. The population that emerges from the bottleneck is genetically less variable than the population that entered it, and this reduced diversity persists for a long time, only slowly rebuilding through new mutations. When geneticists examine human DNA, they find that compared to other great apes, we have remarkably low genetic diversity. This was noticed as far back as the 1970 seconds, even before we had the ability to sequence entire genomes. Studies of blood proteins showed that humans were unusually uniform compared to chimpanzees or gorillas. As DNA sequencing technology improved, this pattern was confirmed again and again. Humans show the signature of at least one severe bottleneck, and probably several smaller ones, in our evolutionary history. The most recent and severe bottleneck seems to have occurred sometime in the late Pleistocene, with different studies giving slightly different dates depending on which parts of the genome they analyze and what assumptions they make about mutation rates. But many estimates cluster around 50,000 to 70,000 years ago. Initially, this timing seemed to match Toba perfectly. The eruption at 74,000 years ago, a genetic bottleneck around 70,000 years ago, it seemed too close to be coincidental. This became one of the key pieces of evidence supporting the Toba catastrophe theory. But as more data has accumulated, the picture has become more complex. Different human populations show somewhat different bottleneck signatures. African populations show evidence of a bottleneck, but it appears to have been less severe and may have occurred slightly earlier than the bottleneck seen in non-African populations. Non-African populations show a very severe bottleneck, with effective population sizes crashing to perhaps only 1,000 to 3,000 individuals around 50,000 years ago. This bottleneck is associated with the out-of-Africa dispersal, when a small group of humans left Africa and eventually colonized the rest of the world. So we're looking at potentially multiple bottlenecks happening at slightly different times for different populations. This makes it harder to link any single event, including Toba, to the genetic signal. There's another complication. The effective population size detected by genetic methods is not the same as the actual census population. Effective population size is a statistical concept that refers roughly to the number of individuals who are actually contributing genes to the next generation. In practice, this number can be much smaller than the total population. If, for example, a population is structured such that only a few males do most of the breeding, or if there are many isolated subpopulations with limited gene flow between them, the effective population size can be quite small even if the actual number of people is much larger. Some recent models suggest that the genetic bottleneck signature we see in modern humans could be explained by population structure and the out-of-Africa dispersal without needing to invoke a catastrophic die-off from Toba. But this doesn't mean Toba had no effect. Even if it didn't cause the bottleneck by itself, it could have contributed to population stress, could have influenced which populations survived and which didn't, could have shaped the distribution of human populations in ways that affected later dispersals. There's also interesting evidence from other species. Genetic studies of chimpanzees show evidence of a population bottleneck around the same time period. So do orangutans. In fact, several African mammal species show this pattern. This suggests that something was affecting multiple species simultaneously, which is consistent with the idea that a major environmental perturbation, possibly Toba combined with natural climate change, was creating widespread stress across ecosystems. One of the most fascinating genetic discoveries related to this period involves what didn't happen to humans. During the severe stress of the Toba period and its aftermath, With populations fragmented and isolated, you might expect genetic drift to cause different human groups to diverge significantly from each other, perhaps even to the point of becoming distinct subspecies. But that didn't happen. Despite the bottlenecks and the geographical separation, all modern humans remained part of a single species. When we eventually did expand out of Africa and spread around the world, we maintained enough genetic compatibility that populations could and did interbreed when they encountered each other. This suggests that despite the stress, despite the population crashes, there was still enough gene flow between groups to maintain genetic cohesion. The social networks we discussed earlier weren't just important for risk buffering and resource sharing, they were also important for maintaining genetic connectivity. Another intriguing genetic signal from this period involves selection, the process where certain genes become more common because they provide a survival advantage. When researchers look for signs of positive selection in the human genome, for signals that certain genetic variants spread rapidly through populations because they improved fitness, several interesting patterns emerge. Some genes related to brain development show signs of selection during the late Pleistocene. This could be coincidental, or it could suggest that the challenges of this period, including Toba, favored individuals with certain cognitive advantages. Similarly, genes related to immune function show selection signatures. This makes sense in a world where populations were stressed, living in close quarters, potentially dealing with novel pathogens as they moved into new environments or encountered other human groups. But perhaps most interestingly, some genes related to dealing with environmental stress show evidence of selection. Genes that affect metabolism, that influence how bodies respond to nutritional stress, that affect cold tolerance, all of these show patterns consistent with selection during this period. It's as if we can see, written in our DNA, the echo of our ancestors struggling to survive in a harsher world. The genetic variants that helped them cope became more common, and we carry those variants today. There's also the question of interbreeding with other human species. We now know that modern humans interbred with Neanderthals, probably in the Middle East around 50,000 to 60,000 years ago. We also interbred with Denisovans, probably in Asia around the same time period. These interbreeding events happened after Toba, but during the broader period of climate instability and population stress. It's possible that the challenges of this era, the reduced population sizes and the need to exploit every advantage, made interbreeding with other human species more likely or more acceptable. Some Neanderthal genes that entered the modern human gene pool during these encounters have been maintained at surprisingly high frequencies, suggesting they provided some advantage. Genes related to immune function are particularly common, possibly because Neanderthals, having lived in Europe and Asia for hundreds of thousands of years, had evolved resistance to local pathogens that newly arriving modern humans hadn't encountered before. So the genetic legacy of the Toba period is complex. It's not just a simple bottleneck that we can point to and say, this is from Toba. Instead, it's a layered story of population contractions, dispersals, isolations, and reconnections, all happening against the backdrop of a climatically unstable world. What the genetics do tell us unequivocally is that human populations went through a very challenging time around 70,000 years ago. Whether Toba was the primary cause or just one contributing factor remains debated, but the signal of population stress is undeniable, and yet we survived. The genetic diversity we lost was eventually rebuilt, slowly, through new mutations and through population expansions into new territories. The populations that emerged from the bottleneck went on to colonize every habitable continent, to develop agriculture, to build civilizations, to eventually sequence their own genomes and puzzle out the story of where they came from. In that sense, the genetic legacy of Toba is not just the bottleneck, it's also the recovery, the expansion, the triumph over adversity. Every human alive today is a descendant of those who survived, carriers of their resilience, written into every cell of our bodies. Chapter 8. The debate continues. Science, at its best, is a process of constant revision. As new evidence emerges, as new analytical techniques are developed, our understanding of past events shifts, and refines. The story of Toba and its impact on human evolution is a perfect example of this process in action. When Stanley Ambrose first proposed the Toba catastrophe theory in 1998, it was a bold and provocative idea that tied together multiple strands of evidence: the massive scale of the eruption, the genetic bottleneck, and the apparent coincidence in timing. It was elegant, dramatic, and it captured the public imagination. Here was a story of humanity brought to the very brink of extinction, of our species reduced to a few thousand desperate survivors, of an apocalyptic event that nearly ended our story before it had truly begun. It was compelling, and for many years, it was widely accepted. But science isn't about telling compelling stories. It's about following the evidence wherever it leads, even if it leads to less dramatic conclusions. And as researchers continued to investigate Toba, as they drilled more ice cores and excavated more archaeological sites and ran more sophisticated climate models, the simple catastrophe story began to show cracks. The first major challenge came from the climate side, when researchers tried to replicate the severe, millennium-long volcanic winter suggested by the original theory using state-of-the-art climate models. They couldn't do it. Yes, the models showed significant cooling for several years after the eruption. Yes, they showed major disruptions to precipitation patterns, but they didn't show 1,000-year-long deep freeze. The volcanic aerosols, no matter how massive the initial injection, eventually settled out of the atmosphere. The sun returned to full strength, and temperatures recovered within a decade or two. The longer-term cooling seen in the climate record appeared to be part of natural climate variability, the ongoing transition into glacial conditions that would have happened with or without Toba. The eruption may have amplified this cooling, may have accelerated the transition, but it didn't create it. A 2009 study by climatologist Alan Robock and colleagues was particularly influential. They modelled Toba-scale eruptions with various sulfur emission scenarios and found that while the immediate cooling could be severe, it was also relatively short-lived. Their conclusion was stark. The results virtually eliminate mega-volcanic eruptions as one of the key drivers of global-scale glaciation. Then came the archaeological evidence. Site after site, from South Africa to India, showed continuity of human occupation across the Toba event. The stone tools didn't change dramatically. There was no obvious break in the sequence. People didn't disappear. The discovery of actual Toba ash at sites like Jwalapuram in India should have been the smoking gun proving catastrophic effects on local populations. Instead, it showed the opposite. The same people, using the same tools, living in the same way, before and after. Even the genetic evidence, once thought to be the strongest support for the catastrophe theory, became more ambiguous as more data accumulated. The bottleneck was real, but its timing and severity varied by population, and multiple plausible explanations that didn't require a near-extinction event were proposed. Does this mean Toba was unimportant? Not at all. An eruption that ejected 2,800 cubic kilometers of material, that caused measurable global cooling, that deposited ash across 2 continents, that's still a major geological and potentially ecological event. What's changed is our understanding of its effects and our appreciation for human resilience. The current consensus, to the extent that there is one, is more nuanced than either the original catastrophe theory or a complete dismissal of Toba's impact. Most researchers now agree that Toba was one of the largest volcanic eruptions of the past 2 million years, and certainly had global environmental effects. The eruption caused a volcanic winter lasting several years, and may have amplified an ongoing cooling trend. Human populations were stressed during this period, and did go through at least one genetic bottleneck. But the bottleneck was probably due to multiple factors, not just Toba, including natural climate change and population structure. Human populations were more widespread and resilient than initially thought, with some regions showing continuity of occupation and even innovation during the Toba period. Rather than nearly going extinct, humans adapted their behaviors in ways that helped them cope with environmental stress. This more complex picture is, in many ways, more interesting than the simple catastrophe story. It shows humans not as lucky survivors of an apocalypse, but as adaptable, innovative, resilient people who faced a major challenge and found ways to overcome it. It also raises fascinating questions about the relationship between environmental stress and technological innovation. Several researchers have noted that the period around and after Toba saw significant advances in human technology and behavior. The development of more sophisticated stone tools, the possible invention of bow and arrow technology, increased use of symbolic behavior like personal ornaments, the beginnings of complex trade networks that moved materials over long distances. Did the stress of living through Toba and its aftermath actually drive innovation? Did the challenges faced by our ancestors push them to develop new strategies that would ultimately make modern humans more successful than other human species? This is a difficult question to answer definitively. Correlation doesn't prove causation, and we have to be careful about creating just-so stories. But the timing is intriguing, and the idea that adversity can drive innovation is well established in other contexts. There's also ongoing debate about the effects on other human species. Neanderthals survived Toba. We know this because they persisted in Europe for another 30,000 years. But did the eruption and its aftermath affect their populations? Did it contribute to the demographic changes that eventually led to their extinction? We don't have good enough genetic data from Neanderthals to detect population bottlenecks with the same precision we can for modern humans. But some researchers have speculated that if modern humans weathered the Toba period relatively well by adapting their behavior, while Neanderthals were hit harder and adapted less successfully, this could have been a factor in modern humans' eventual demographic dominance. Similarly, the Denisovans, about whom we know even less, may have been affected differently depending on where they lived. The fragmentary evidence we have suggests they inhabited areas that would have been significantly impacted by both the eruption and the subsequent climate deterioration. As the debate continues, researchers are developing new ways to investigate these questions. Ancient DNA technology is constantly improving, allowing us to extract and sequence genetic material from older and more fragmentary remains. This is giving us direct glimpses into the genetic diversity of past populations rather than having to infer it from modern samples. New archaeological techniques are allowing us to detect subtle changes in behavior that might not leave obvious physical traces. Detailed analyses of residues on stone tools, for example, can reveal what they were used to cut, providing information about diet and resource use that goes beyond what we can learn from animal bones alone. And climate science continues to advance. Higher resolution climate proxies, better understanding of how different climate drivers interact, more sophisticated modelling. All of these are helping us build a more detailed picture of what the environment was actually like during the Toba period. One area of particular interest is the regional variation in Toba's effects. While global average temperature is one thing, what really matters for populations is local conditions, and these varied widely. Some regions may have experienced severe cooling and drought. Others may have seen increased precipitation as atmospheric circulation patterns shifted. Some areas that were previously habitable may have become too harsh, while other areas that were marginal might have become refugia, where conditions remained tolerable. Understanding this regional variation is key to understanding how different human populations fared. It's possible that populations in some regions were devastated while those in other regions were barely affected. This could explain the somewhat contradictory evidence, with some sites showing disruption and others showing continuity. There's also growing interest in the idea that the Toba period might have been a time of increased cultural exchange and innovation driven by necessity. As populations moved and concentrated in refugia, different groups that had been isolated may have come into contact. This could have led to the exchange of ideas, technologies, and genes. Some researchers have suggested that the challenges of this period might have favoured certain cognitive traits, creating selection pressure for enhanced social learning, improved communication, or better planning and foresight. These traits would have been advantageous for dealing with unpredictable environments and resource scarcity. If true, this would mean that Toba and the broader period of climate instability didn't just test human adaptability, it actively shaped it, molding our ancestors into the highly flexible, innovative species we became. But we should be cautious about overinterpreting the evidence. The archaeological and genetic records from this period are still fragmentary. Many regions have been poorly sampled or not sampled at all. New discoveries could dramatically change our understanding. What we can say with confidence is that the simple catastrophe story of Toba, nearly exterminating humanity, is almost certainly wrong. But exactly what happened, how different populations were affected, what role Toba played versus other factors, these remain active areas of research and debate. And perhaps that's how it should be. Science isn't about reaching final, definitive answers. It's about progressively refining our understanding, about following the evidence even when it leads to more complexity rather than simple certainty. The story of Toba and human survival is still being written. Every new archaeological site excavated, every new ancient genome sequenced, every new climate model run adds another piece to the puzzle. And slowly, patiently, we're assembling a picture of what might have been the most challenging period in modern human history and how our ancestors rose to meet that challenge. Chapter 9. Lessons for Today. As we've journeyed through the story of Toba, from the cataclysmic eruption itself to the evidence of human survival and adaptation, you might be wondering, why does this matter? Why should we care about an event that happened 74,000 years ago? There are several reasons, some practical, some philosophical, all of them relevant to our present moment. First, there's the simple fact that supervolcanoes like Toba still exist, and they will erupt again. The question is not if, but when. And while we can't predict exactly when the next super eruption will occur, we can be certain that it will happen at some point in the future, whether that's 1,000 years from now or 100,000. There are at least 20 known supervolcano systems around the world capable of producing VEI-8 eruptions. Some are well known, like Yellowstone in the United States or Taupo in New Zealand. Others are less famous but equally dangerous. These systems are monitored, but our ability to predict eruptions is limited, especially for events on this scale that occur so rarely. When the next super eruption does occur, understanding what happened during Toba can help us prepare. We know now that the effects won't be uniform globally. We know that regional climate responses can vary. We know that certain areas might serve as refugia, while others become uninhabitable. This knowledge can inform disaster planning, help us identify which regions are likely to be most severely affected, and potentially guide decisions about where to establish food reserves or plan evacuation routes. But more importantly, studying Toba teaches us about resilience, about how societies can survive when faced with planetary-scale disasters. The key lessons from human survival of Toba are: flexibility matters more than specialization. The populations that survived Toba were those that could adjust their subsistence strategies, that could exploit multiple types of resources, that could move when necessary. In today's context, this suggests that building resilient societies means maintaining diversity in food systems, in energy sources, in technologies. Putting all our eggs in one basket makes us vulnerable. Local knowledge is crucial. Our ancestors survived because they had deep knowledge of their local environments. They knew where to find water even in droughts, which plants could be eaten when others failed, how to read the signs that indicated where game might be found. Today, this translates to the importance of indigenous knowledge, of local ecological expertise, of not losing traditional practices that embody generations of environmental wisdom. Social networks provide buffering. The evidence suggests that maintaining connections with other groups, through trade, through social ties, through occasional interbreeding, helped populations survive. Isolated groups were more vulnerable. This has obvious parallels to modern disaster response, where international cooperation and mutual aid can mean the difference between recovery and collapse. Innovation accelerates under pressure. Some of the most significant advances in human technology and behavior occurred during periods of stress. The challenges our ancestors faced pushed them to develop new strategies, new tools, new ways of organizing themselves. This is a hopeful message. It suggests that human ingenuity rises to meet challenges, even severe ones. Recovery is possible but slow. The genetic bottleneck created by Toba and the broader period of climate instability took thousands of years to reverse. Populations didn't bounce back immediately. This is a reminder that while societies can survive catastrophes, the path to full recovery is long and uncertain. There's another, more immediate reason why the Toba story matters. It provides context for understanding anthropogenic climate change. We're currently conducting what amounts to a massive, uncontrolled experiment on our planet's climate system by burning fossil fuels, by releasing greenhouse gases, by altering land surfaces. We're changing the global climate at a rate unprecedented in human history, and perhaps unprecedented in Earth's history, outside of catastrophic events like asteroid impacts or super eruptions. The changes we're causing are different from those caused by Toba. We're warming the planet rather than cooling it, but the principle is the same: rapid, anthropogenic environmental change that ecosystems and societies must adapt to or perish. Studying how our ancestors responded to Toba's climate effects can provide insights into how modern societies might cope with climate change. What strategies worked? What didn't? How did populations reorganize in response to changing conditions? Of course, the analogy is imperfect. Our ancestors were small-scale hunter-gatherer bands. We're a global civilization of 8 billion people with complex infrastructure and intricate supply chains. The challenges are different in scale and kind, but the fundamental issue remains the same. How do we adapt to a rapidly changing environment? How do we maintain social cohesion during times of stress? How do we ensure that the most vulnerable populations aren't left behind? The Toba story also speaks to something more philosophical, to questions about human nature and our place in the natural world. For much of our history, we've seen ourselves as somehow separate from nature, as controllers of our environment rather than participants in it. We've imagined that our intelligence and technology elevate us above other species, make us immune to the constraints that govern other life forms. But Toba reminds us that we're still part of the Earth system, still subject to its whims, still vulnerable to its catastrophes. A single volcanic eruption nearly ended us. Not through any malicious intent. The volcano wasn't targeting humans, but simply as a side effect of natural geological processes that have been occurring for billions of years. This is humbling, but it's also oddly comforting, because if our ancestors, with their simple stone tools and their small, scattered populations, could survive Toba, then surely we, with all our knowledge and technology, can face the challenges of our own era. But we have to be smart about it. We have to learn from the past. We have to build resilient systems that can weather shocks. We have to maintain the flexibility and adaptability that allowed our ancestors to survive when so much else perished. There's also a question of perspective that the Toba story brings into sharp focus. In the grand sweep of Earth's history, in the billions of years the planet has existed, humanity is a newcomer. Modern humans have been around for maybe 300,000 years. Anatomically modern humans who were behaviorally modern, who had art and complex tools and everything that makes us us, have only existed for perhaps 100,000 years. Toba occurred just 74,000 years ago. Within the span of modern human existence, it's part of our history, part of what shaped us into who we are. And yet, from our perspective, trapped as we are in the brief span of a human lifetime, 74,000 years seems like an eternity. It's almost impossible to wrap our minds around that much time. The oldest human civilizations, the first cities and kingdoms and empires, only date back about 10,000 years. Everything we think of as history, all the wars and migrations and rises and falls of nations, all of it has happened in just the last few thousand years. Toba is ancient beyond our normal frame of reference, and yet, geologically speaking, it's recent. The rocks still remember. The evidence is still there, waiting to be found and interpreted. This dual perspective, human timescales versus geological timescales, is important to maintain. On human timescales, The next super eruption might be unimaginably far in the future, something our children's children's children 100 generations hence might have to deal with. But on geological timescales, it's right around the corner, and the more we can learn from past events, the better prepared we'll be when it inevitably occurs. Finally, and perhaps most importantly, the Toba story is fundamentally hopeful. Yes, it's a story about catastrophe, about the planet conspiring to kill us, about survival hanging by a thread. But it's also a story about resilience, about adaptation, about human ingenuity and social cooperation seeing us through the worst conditions imaginable. We survived. Against odds that seem impossible from our comfortable modern perspective, our ancestors endured. They didn't just survive, they thrived, they innovated, they expanded, they eventually conquered the planet, spreading to every habitable continent, developing agriculture, building civilizations, reaching the point where we could look back and puzzle out the story of where we came from. Every human alive today is a testament to that survival, a living monument to the resilience of those ancient bands huddled around fires under darkened skies, wondering if the world would ever return to normal. The answer, of course, was no. The world didn't return to normal. It changed, and our ancestors changed with it. They adapted, they evolved, not biologically so much as culturally and technologically. They became who we are, and if they could do that, if they could face planetary catastrophe with nothing but stone tools and fire in each other, then what can't we do? What challenges can't we overcome if we're willing to be flexible, to innovate, to support each other, to draw on the same resilience that carried our species through its darkest hour? That's the real lesson of Toba. Not that we're vulnerable, we already knew that, but that we're also capable of extraordinary things when we have to be. That human ingenuity and adaptability are not just abstract traits, but real forces that have shaped our history and can shape our future. As we face the challenges of the 21st century, from climate change to pandemics, to the possibility of future natural disasters, we would do well to remember the story of Toba, to remember that we've been here before, that our ancestors faced an impossible situation and found a way through. We carry their resilience in our genes, their innovation in our culture, their survival in every breath we take. And if we can tap into that same adaptability, that same flexibility, that same determination, then perhaps the challenges ahead, daunting as they may be, are not insurmountable after all. Chapter 10. Reflections in Deep Time. As we near the end of our journey through the Toba story, it's worth taking a moment to step back and reflect on what we've explored tonight. We've travelled 74,000 years into the past, to a time when the world was colder, when ice sheets covered much of the northern hemisphere, when our ancestors lived in small, mobile bands scattered across Africa and parts of Asia. We've witnessed one of the most catastrophic volcanic eruptions in Earth's recent history, an event so massive that it ejected enough material to bury entire countries, that darkened the skies and cooled the planet for years, that left its mark in ice cores in Greenland and Antarctica, in ash layers across 2 continents, in the genetic code of every human alive today. We've followed the evidence trail, from microscopic shards of volcanic glass to sophisticated genetic analyses, from climate models to archaeological excavations. We've seen how science is a process of constant revision, how simple stories give way to complex ones as more data accumulates. And we've met our ancestors, not as primitive cavemen, but as sophisticated, adaptable, resilient people who faced unimaginable challenges and survived through a combination of technological innovation, social cooperation, and sheer determination. The story of Toba is many things. It's a geological tale about the awesome power contained within our planet, about forces that dwarf human concerns, but that we must nevertheless contend with. It's a biological story about population dynamics, about bottlenecks and founder effects, about how small groups can recover and spread to fill the world. It's an archaeological story about how we piece together the past from fragmentary evidence, about how tiny details, a shard of glass, a stone tool, a layer of ash, can reveal vast dramas, when properly interpreted. But most of all, it's a human story about who we are, where we came from, and what we're capable of when pushed to our limits. When you look out at the world around you, when you see the vast numbers of humans, the cities and infrastructure and technology that blanket the globe, it's easy to forget how precarious our existence once was. Easy to forget that there was a time when all of humanity could have fit into a small town, when our future was anything but assured. But 74,000 years ago, that was our reality. We were an endangered species, a marginal population barely clinging to existence in a world that seemed determined to erase us. And yet, here we are, 8 billion strong, masters of every environment from tropical rainforests to Arctic tundra, the most successful large mammal species the planet has ever seen. That transformation, from endangered to dominant, from barely surviving to thriving, took time, tens of thousands of years, hundreds of generations, but it happened because our ancestors refused to give up, because they adapted when they needed to, because they remembered, in their stories and their traditions and their accumulated knowledge, how to survive when the world turned harsh. In a sense, every one of us alive today is a message sent forward through time by those who survived Toba. We are their legacy, their victory over impossible odds, the proof that they succeeded where so many others failed. And perhaps that's worth contemplating as you drift off to sleep tonight, that you are part of an unbroken chain of survivors stretching back not just generations, not just millennia, but tens of thousands of years, that every ancestor you've ever had, going back to those huddled around fires under ash-darkened skies, managed to survive long enough to reproduce, that you carry within you the distilled wisdom, encoded in your genes and your culture, of how to endure. There's a peculiar poetry to the fact that we can know this story at all, that we can look back across such vast expanses of time and reconstruct what happened, that we can find particles of glass smaller than a human hair and use them to understand planetary catastrophe, that we can read the book of life written in our DNA and see the echoes of ancient bottlenecks. We are, in a very real sense, the Earth becoming conscious of its own history. Through us, the planet looks back at itself, understands its own past, marvels at its own complexity, and in that understanding, in that marvel, there's a kind of redemption for all the suffering and struggle of the past. The people who lived through Toba didn't know their survival would be remembered, didn't know that tens of thousands of years later, their descendants would piece together their story and honor their resilience. But we do know, and we do remember, and in remembering, we make their struggle meaningful. We ensure that their survival was not in vain. As you lie there in the darkness, imagine those ancient humans looking up at the same stars we see, though perhaps dimmed by ash, perhaps strange in the hazy sky. Imagine them wondering, as we wonder, about their place in the cosmos, about whether they would survive, about what lay ahead. They couldn't have imagined us, their distant descendants, with our technology and our vast cities and our ability to look back and see them as they were. They were focused on the immediate challenge, on finding food, on staying warm, on protecting their families. But in doing those simple, necessary things, in just refusing to give up, they set in motion a chain of events that would lead, eventually, to us, to this moment, to you, listening to this story in the comfort and safety they could barely have dreamed of. That's the wonder of deep time. It's not just about the past being far away, it's about connection, about continuity, about the recognition that we're part of something larger than ourselves, a story that began long before we were born and will continue long after we're gone. The Toba story doesn't have a tidy ending because it's not really ended. We're still living it, still carrying the legacy of those who survived, still facing challenges that test our adaptability and resilience. The specific challenges have changed. Of course, we're not worried about volcanic winters or where to find the next meal, but in a deeper sense, we're facing the same fundamental question our ancestors faced. How do we survive in a world that can be harsh and unpredictable? How do we build societies that can weather shocks and endure? The answer, if there is one, probably lies in remembering what worked before. Flexibility, cooperation, innovation, local knowledge combined with wide-ranging networks, the willingness to change when circumstances demand it. These aren't just historical curiosities, they're practical lessons. And as we face the challenges of our own era, whether they're climate change or pandemics, or the countless other threats that can emerge in a complex world, we would do well to remember that we come from survivors. That survival is, in a sense, our birthright. Not guaranteed, never guaranteed, but possible, always possible. So let that thought accompany you as you drift towards sleep. You are part of an unbroken chain. You carry within you the accumulated wisdom of 100,000 generations. You are a survivor, because everyone who came before you survived long enough to pass life forward. And tomorrow, when you wake, you'll carry that survival forward one more day, one more link in the chain, one more breath in a story that stretches back to the darkest skies and forward to horizons we can barely imagine. The ash has long since settled. The skies have cleared. The world that emerged from Toba's shadow was forever changed, and so were we. We became more than we were before. We became ourselves. And in that becoming, in that transformation through catastrophe, we learned the most important lesson of all, that we are capable of surviving anything, as long as we're willing to adapt, to innovate, to support each other through the darkness until the sun returns. Sweet dreams, survivors. May you rest well, knowing you're part of a story that began in fire and ash and endured to see countless dawns. Thank you for joining me on this journey through deep time to one of the most crucial moments in human history. Thank you for your curiosity, your patience, and your willingness to explore these vast, ancient stories. If you enjoyed this exploration, please consider liking the video and subscribing to the channel. Your support helps make these deep dives possible and helps this channel reach other curious minds who want to understand where we came from and what we're capable of. Until next time, rest well, and remember, you're here because your ancestors never gave up. Never forget what that means. Good night.